this class today, this morning. Okay, so I think what we did last time was ODE, right? ODE. So let's review what we have done so far. What we have done so far. So because I want to continue still today in the topic of ODE. Okay. Excuse me. Ini saya batuk pula. So mungkin terhenti-henti lah saya punya percakapan. Alright, never mind. So why not we continue. So let's go over what we have done so far. And let me share with you my piece of paper here. Okay, so where is it? Share. Okay, so let's review what we have done so far. So I think this is another continuation from the topic of ODE. Okay, so we started with ODE. And we say that ODE is just simply that dy, for example, dy dx equal to a function. Okay, where dy dx is the slope. So we say that when we try to approximate this using numerical method, so that dy is just basically dy dx. So what we can say is dy dx is approximately delta y over delta x. And in this case, we can substitute, and what we have here is delta y delta x equal to fx y, or this is just yi plus 1 minus yi equal to fx y times delta x, as we define delta x as h, okay, which is the step size. So this simplified to yi plus fx y plus h. So this is commonly known as our Euler's method. Euler's method. Okay, very simple, very straightforward. And what we can see here is okay, and we say that always in the case of numerical method, the first step to do is to approximate. The second step is to improve the approximation. So in this case, we know that this is our step size. H is our step size. And our fxy is our slope, right? So one way to improve is that what we want here is to we say one way improvement. What are the steps for improvements? We say one is make h smaller. Smaller h will increase the accuracy. Will increase the accuracy. That's one. And the other way is the only variable here in this case is this, which is 2. We say improve slope estimation. Okay, so that's the first step. No, that's the second step. And I think we talk about this. We say that we started with Euler method, which is this one, Euler's method, and we try to improve Euler's method. And what we found is that we have in this case for slope estimation, we have the midpoint method. Okay, and then we also have what we call the Hewan's method. And of course, the other one is RK method, Rangga kata method. Okay, so these are the improvement of the slope estimation. And then we concentrate on RK method. We concentrate on RK method. And I think in your textbook, if you read your textbook, it says that in the RK method, we have discussed about RK1, which is first order RK method, then RK2, and then RK3, and then RK4. Okay, RK1 is basically your Euler's method. And then RK2, in your textbook, it mentioned about three methods. Three methods, depending on the parameter that you use for your, I think for your A, P, and so on. So one is midpoint, Hewens, and the other one is Ralston. Ralston. So basically, our Hewens method and midpoint method is RK2, is under RK2 method, and we can see that midpoint and Hewens method is a better estimate than using just Euler method, because Euler method is first order. It's first order RK1. Okay, and then RK3, I don't think we talk about this, but it's in your textbook. Yeah? And then we have RK4. RK4 also, there are several methods, but the common one is what we call classical RK4. And I think in your project, you have to use Euler method, Hewens method. I don't remember, either Hewens or midpoint, and then RK4. And then you want to compare the accuracy of all these three. So I've done so far with ODE. So note that in this case, this is a first order ODE. And then I think last week we talked about second order ODE. Second order ODE. So how do we solve second order ODE? I think we have some examples I presented last week in class. So second order ODE, if I'm not mistaken, we started with a system of ODE. For example, so there are categories in this case. So we have second order ODE. First, we have system of ODE. System of first order ODE. Okay. Okay, system of first order ODE. So the example that I gave you last time was dy1 dx equal to minus 0.5 y1. Okay, and then dy2 dx equal to 4 minus 0.3 y2 minus 0.1 y1. Okay, note that this equation, these two equations, okay, has two unknowns. Has two unknowns. This one, for example, the second equation has two unknowns. So note that in this case, it's not only y2 as our unknown, y1. So we need to solve the first equation first, then we can find our second equation. So what we can do is to solve this simultaneously. So in this case, what we can see is that y1 I plus 1 equal to y1 I minus 0.5 y1 I times h. Okay, note that we can find, if we know what is y0, okay, we know y0, which is in this case equal to our our y0 is the initial condition, which is equal y0, then we can find what is y1. And the result for this case, in this case, what we can write here is, for example, for the first iteration, y1 or first iteration equal to y1 naught equal to 0.5 y1 naught times. Okay, so this is y1. So if we solve for the second one, we can see that this is y2i plus 1 equal to y2i plus 4 minus 0.3 y2i minus 0.1 y1 I times h. And for the first iteration, we know that this is just y2 1 equal to y2 naught plus 4 minus 0.3 y2 naught minus 0.1 y1 naught times h. Note that in this case, y2 naught equal to y2 at initial condition. Yeah. So note that in this case, this is a second order ODE, right? This is a second order ODE. Oh, sorry. This is a it's a system. It's a system of two first order ODE. So what we need is every ODE, every first order ODE must have one initial conditions. So for the first equation, this one is y1, y1. So for this, we have this as initial condition. For this, we have this for the initial condition. Note that we can solve this because we know that this value from the initial condition of y1, and we also know this from the initial of y2, initial condition of y2, and this is for the initial condition of y1. So now we can continue because let's say this is now y1, the second iteration, then this is y1 minus 0.5, y1, 1, and h. So this one come from this, okay? So this. And now the same thing for this, which is y. Now this is the second iteration, so this is 2, 1 plus 4 minus 0.3 y2, 1 minus 0.1 y1, 1, and h. Note that this value is also used here, and this is used here and here. And I think I did the Excel sheet last time, and I get this solution. Let me share with you my Excel here. Okay, so this is the calculation. So to find y1, we need y0 iteration, initial condition. To calculate y2, we need not only y2, the initial condition, but also y1 initial condition, which is, if you look at this, the formula requires this and this. Okay, so this is the formula. This is the formula. So I make it simple because I use Excel in this case. Now, let's continue. So there are two second order ODE, and the first one is basically system of two first order ODE. And then the second one is, of course, one second order ODE. One second order ODE. And I think what we did was this equation, which is dyt d square y d t square minus t plus y equal to 0. Okay, so look at this. This is definitely a second. And note that because this is second order ODE, it needs two external conditions. We call this initial condition. For example, I think the initial condition is that at y at t equal to 0 is 2, and dy dt at t equal to 0 is equal to 0. These are the conditions. These are the initial conditions given. So now we need to split this. We need to convert this to two one order, two first order ODE. So I think what we did last time was dy, let dy dt equal to z, and then we know that then d square y dt square, okay, it's just d dt of dy dt, which is just dz dt. Okay, and then so we substitute this, and this is our, okay, so this is our first equation, and our second equation is just substitute this into d square y dt square minus t plus y equal to 0, which is now become d square y dt square is just dz dt minus t plus y equal to 0. So the two first order ODE becomes dy dt equal to dy dt equal to z, and then dz dt equal to t minus y. Okay, so these are the two first order ODE, and I think we know how to solve this because we solved this before. System of first order ODE, right? So this is just becomes the system of ODE, system of ODE. So very straightforward, very straightforward. So what we can do here is just again use this. I'm using Euler's rule, using Euler's method. Of course, you can use a lot of other methods. You can use Yuan's method or so on, but for the sake of just an example here, I'm using Euler's method because this is very quick. So we know that from the first equation, our yi plus 1 is just equal to yi plus zh. Okay, plus zi h. And then from the second equation, this is zi plus 1 equal to zi plus t minus y times h. So ti yi times h, where our boundary condition is again, so dy dt is just our boundary condition in this case is that y at t equal to 0 is equal to 0, sorry, not 0, equal to 2. And our second boundary condition is dy dt is our z. So t at t equal to 0 equal to 0. So these are the boundary condition. These are the equation. So we know that in this case, our y0 equal to 2 and our z0 equal to 0. So we can solve this. And of course, I have my Excel sheet here that I can share with you. And you can see that this is the solution. This is the solution. Okay, so this is our second order ODE. Now, let's go a little bit more. So let's look at this equation. This is from your textbook, chapter 27. Chapter 27. And I don't remember the page. This is figure 27.2 from your textbook. So, okay. I'm running. Okay, so what we can do here, let me add more papers here because I'm running a lot of papers. Okay, now let's solve this kind of problem. So this is figure 27.2 from your textbook. From your textbook. And this problem here equal to 0, and this is x equal to L. And we have at x equal to 0, we have T1, temperature 1, and we have temperature, let's say temperature 3. So in your textbook, this is temperature 2. Okay. Temperature, okay, never mind. Let's use the same notation as your textbook. So this is your T2. So basically, the temperature at x equal to 0 is known. The temperature of x equal to L is known. So in this case, we know that T at x equal to 0 is equal to T1, and T x equal to L is equal to T2. So these are known, known values. Known values. Okay, these are known values. All right, so okay, so now, so this is the problem. So what we want to know now is to find the temperature in between x equal to 0 and x equal to L. So in the governing equation, this is given as the heat transfer law. I think this is what we call Laplace equation, if I'm not mistaken. D square T dx square plus h prime, okay, Ta minus T equal to 0. Note that, again, this is a second order ODE. It's a second order ODE. So how do we solve this kind of problem? How do we solve this kind of problem? Okay? How do we solve this kind of problem? So note that this is not the same one as before. This is not the same one as before because the nature of the problem is not the same. The nature of the problem is not the same. First, we must realize that if you recall whatever you learned in your math, your ODE class, ataupun I think they call it persamaan terbitan. Second order ODE, second order ODE has two types. First, The first one is what we call the initial value problem. And the second one is what we call the boundary value problem. Okay, initial value problem, or commonly known as IVP, and boundary value problem is BVP. Okay, note the key word here is the initial value and the boundary value. Note that our previous example is that it is the boundary condition, or sorry, the condition, what we call the external condition, is defined at t equal to 0 and t equal to 0. And this one, okay, and this one is also defined at x equal to 0, x equal to 0, right? So they are defined at one particular value sahaja, x. In this case, the x is equal to 0. Okay, and this one is also defined at x at t equal to 0. The first condition is at t equal to 0. The second condition is also at t equal to 0. So the two conditions are defined at the same dependent variable. Sorry, the same independent variable. Okay, the two values, the two conditions are defined at the same dependent variable. In this case, t equal to 0, and in this case, at x equal to 0. And if you look at the next problem here, note that our two conditions here are defined at different independent variable. In this case, at x equal to 0 and x equal to L. Okay, definitely if you look at the diagram, you know that they are defined at this location and at this location, which are the boundary of the problem. Okay, which are the boundary of the problem. And because of this, this is what we call a boundary value problem. Okay, so this one is our BVP. And this one is our IVP. And this is our IVP. So you must be able to differentiate or to tell which one is IVP and which one is BVP. If not, you get incorrect answers. Why? Because in the test, it will not tell you this is a BVP or IVP. You need to understand which one is which. Which one is which? Which one is which? So, and how do we solve this kind of question here? How do we solve this boundary value problem? Okay, it has a different method. So BVP cannot be solved using Euler's method. Cannot be solved using Euler's method. So this, if you do not understand which one is BVP, which one is IVP, then you use the wrong method for the wrong problem. That's it, you are done. Okay, the answer will not be correct. Okay, so in this case, since this is a BVP, if you look at the textbook, there are generally two methods, but we are going to concentrate on only one method. Okay, the first method is what we call shooting method. I don't like shooting method because it is guessing. It is more of a guessing kind of solution. And the second one is what we call finite difference method. Finite difference method. So we talk about finite difference method here. So note that in this case, in this equation, we can approximate what is dx square d square t dx square. Okay, so what is the approximation here? What is the approximation here? What is the approximation here? Anyone? What is this? What is this? G squared T dx squared. What is this? This is just the second derivative. I think we've seen this before, right? So how do we approximate this? How do we approximate this? Anyone? Anyone? Oh, come on. Test is coming soon, eh? I'm worried. I'm worried. I'm worried, eh? Kamu yang ambil test, saya yang risau. Aduh, hai. So, how do we approximate this? Anyone? Anyone?
Yes.
Hmm?
Doctor? Yeah.
Yeah.
Two ODEs you mentioned last class, right?
Yeah.
Yeah, we can do it here. Two ODEs.
So this one, this you can approximate this using 2 ODE.
This is just like, you know, yes, maybe. I think we can.
No. This
No?
this is derivative. This is not ODE. This is derivative.
Oh.
The question is, how do we approximate this derivative here? This is second derivative, right?
Yes.
Okay, so how do we approximate this? Okay, that is the question here. Okay, ODE is a complete equation. Okay, so I think I understand what you're trying to do here, but for this one, right, this is a complete equation. So you say, okay, split it into 2 first order ODE, right? But no, in this case, I'm not talking about the whole equation. I'm talking about only the derivative. How do we approximate this? Note again, this is boundary value problem. The previous one was initial value problem. So, so how do we approximate this? Okay, how do we approximate the second derivative here? All right, so this is kind of sad, but never mind. I'm just hoping for the best here. Anyway, I'm not taking the test, you are. So let me open up your textbook and hopefully you know where to find it. Okay, this is your textbook. So basically, I don't think you guys read any of the text. Remember the first week I reminded you need to read your textbook. But unfortunately, I don't think you guys read your textbook. Tak apalah. I don't care. I'm not taking the test. You are again. You are taking the test. So I think this is chapter. Where is it? Curve fitting, interpolation. Okay, so look at numerical differentiation here. And note that, I think we talked about this last time. Note that the second derivative can be approximated by all these formulas. Okay, this is forward finite difference. Okay, so for the second, for the first derivative, for the second derivative, this is the one. Okay, for forward finite difference, and then we have backward finite difference. So this is the second derivative, and the other one here is this one here. This one here. Okay, this one. Second derivative, and this is centered finite difference. So we can use this as our approximation. Note that in this case, you have a lot of variation. You have forward difference, you have backward difference, you have centered difference. The only difference is that in this case, for centered difference, it will use one value forward and one value backward. If you want to find this, you need to know the forward and the backward value. Okay, so in this case, I'm going to use my centered difference. The centered difference. Okay, the centered, oh, centered difference, yeah. The centered difference, yeah. So d square t dx square. So what was the formula? I closed it just now. So, okay, so it can be approximated as the forward value minus the current value plus the backward value. What happened? Okay, so I got kicked out from my software. Okay, so let's reshare this. Let's reshare this. Okay, so this is the forward value minus the current value plus the backward value divided by delta x squared. Okay, so now what I'll do is just substitute this
Doctor,
into this
we
equation.
still cannot see.
Oh, sorry, I haven't shared this. Yeah, sorry. Because I was kicked out just now. So let's share this back and okay. So this is the formula. So this is the formula. So I just used the finite difference table just now. So this is the forward value, the current value, and the previous value times over delta x squared. So this is the approximation. And what we can do is just substitute this approximation into this equation. Okay, so now this becomes ti plus 1 minus ti plus ti minus 1 over delta x plus h prime ta minus t equal to 0. This one is ti. This one should be, I think I made a mistake here. It should be ti minus t. What's the formula here? Oh, okay. So, okay. That's correct. Never mind. That's correct. So now this is ti. This is ti. So let's define what is h prime. H prime is the material property. H prime is the material property, which is 0.01. And T ambient, TA is 20. T is 20. So let's go back to my problem here. Okay, so my temperature here is known. So in this case, my T1, my temperature at T1, location 1 is 40 degrees C, and the 40 degrees C, and at T2 it is 200 degrees. Okay, now, and note that this is 10 meters. 10 meters. So this is the notes here. So can I find the temperature at the midpoint here? Can I find this one? So note that in this case, I know, so this is 5 and 5, 5 and 5. So in this case, I can just use this equation. So which is, let's say this is node 0, node 1, and node 2. So if I substitute this number, and when I equal to 0, what I can see here is, oh, sorry, this is wrong. This is wrong. This should be node number 1, node number 2, node number 3. So we know that our T1 equal to 40, T2 is an unknown, T3 is 200. Note that there is only one unknown here, yeah? So we need only one equation in this case. So note that now, in order to find T2, okay, so let's say I equal to 0, then we know that Ti plus 1 is just T1 minus 2T2 plus 2, 2, sorry, I think this is wrong again. Uh, this is wrong, eh? Sekejap, eh? Let me think. Oh, I think this is correct. This is correct. So let's say this is 0, 1. The notation is kind of okay. I think I have a video on this. You can watch the video. I put it on the e-learning, but this is the same thing as is in the video. So now let's say this is our T0. T0 is 40, T1 is an unknown, and T2 is 200. So now I equal to 0, then we say this is T1. Again, I'm sorry because I don't think this is correct. I don't think this is correct. But what we can see here, if we need to find, this temperature value here, we need to know the one previous, the one step backward, and the one step forward. So using this equation, we can solve because we know what is the value forward, T forward. In this case, the T forward is this, and T backward, which is this. So we can solve for this one. Okay, because the rest are known. So this is the method. This is the method. So if you look at your textbook here, example 27.3, example 27.3, and if we use the same equation, okay, if we use the same equation, what we can simplify is that it will becomes minus, let's do this. Ti plus 1 just now, Ti plus 1 minus 2Ti plus Ti minus 1 over delta x square minus h Ta minus Ti equal to 0. And then when we simplify this, what we get is minus Ti minus 1 plus 2 plus h prime delta x square times Ti minus Ti plus 1 equal to h prime delta x square Ta. Note that all these values are known. H prime is given, delta x is your dimension x, and then your Ta is the ambient temperature. So what is not known is this value here. So if we set, okay, T0 equal to 40, T5, before that, let's do, this is the same thing again. So this is our 0, 1, 2, 3, 4, and 5. So T0 is known, which is 40 degrees. T5 is known as 200. And then TA, T ambient, is given as 20. And then H prime is 0.01. And of course, the total length is 10. So we divide by 1, 2, 3, 4, 5, 5 segments, and then our delta X is just 2. It's just 2. So if you do this, let's say I equal to 1, what we have here is minus T naught plus 2 plus H prime delta X T1 minus T2 equal to 0.8. 0.8. Okay, we can keep doing this. I equal to 2. It becomes minus T1 plus 2 plus H prime delta X T2 minus T3 equal to 0.8. Okay, and then I equal to 3. Okay, so I1, I2, I3, I4. I equal to 4. So take a look at this problem here. So how many unknowns here? So this is known as 40 degrees. This is 200. And these are the unknown temperatures, 1, 2, 3, 4. And how many equations do we have here? 1, 2, 3, 4. So we have 4 equations, 4 unknown. And what we can have here is basically, okay, look at this. This is 1, 2, 3, 1, 2, 3. And okay, so if I go to I equal to 4, okay, let me skip. I think I skip. This is T0, T1. This is minus T2. And this one is minus T3. Plus 2 plus H prime delta X T4 minus T5 equal to 0.8. So note that these are just like your simultaneous linear algebraic equation. So if I substitute all the numbers, this is what I get. This is what I get. 2.04 minus 1, 0, 0, minus 1, 2.04 minus 1, 0, 0 minus 1, 2.04 minus 1, 0, 0 minus 1, 2.04. And note these are the unknown temperatures, which is T1, T2, T3, T4, and this is 40.8, 0.8, 0.8, and this one is 200.8. So there are 4 unknowns and there are 4 equations. Can we solve for T1, T2, T3, and T4? Okay, I think you will learn this during your SLE. So this part of the problem is basically using your centered finite difference to find the equations of the unknowns. Okay, and then we set it up in matrix form and solve. So I think the solution is given here as our T, because there are 4 unknowns. So this is 65.69. Sorry, 96. 96. 98. Okay, 93. 7785. 124.5382, and then 159.4795. Okay, so this is ODE, second order ODE value boundary value problem. So remember, second order ODE second order ODE, we have two types. One is IVP, one is BVP. Okay, what's the difference between IVP and VVP? The way the external conditions are defined. So the conditions are, in this case, for example, that y at x equal to 0 is, for example, 2, and y prime, which is or dy dx, in this case dy dx, at x equal to 0 is equal to 0. Note that it is defined at the same independent variable, where BBP, in this case, we define t at x equal to 0 is for t, and the temperature at x equal to 10 equal to 200. So note that the way the location at it is defined are at two different locations. Okay, so this is how you differentiate between IVP and VVP. And note, IVP, the way to solve this is using the simplest one is Euler's, and the other one, which is more accurate, is RK, RK2 and above, RK2, 3, 4, and so on, because RK1 is simply just RK1 is simply our Euler's method. And for BVP, the way to solve this is using two ways. One is shooting method. I think you can read this in your textbook. It's just 1 or 2 paragraphs. Okay. And I think there's also an example in your textbook, shooting method. And the other one is what we call the finite difference. Finite difference. Okay, so normally we use centered finite difference. So note, if you misunderstood which one is IVP and which one is VVP, then you will use the wrong method and you get nothing. Okay, most probably you get nothing. So note that IVP, the method is Euler and its variation. Okay, and then for VVP, there are only two methods, which is switching method or finite difference. So be very careful when you read the question. Be very careful when you read the question. Okay, so before we go, I think I have given you in class assignment, an in-class assignment that I want you to do it. I want you to do in class, and this one is a short assignment. Let me see. Before I share the screen, let me see if this is already posted. Sorry, I think I already posted the thing, so let me turn it on. It is assignment number 9. Assignment number 9. It's not, I don't think you can see it on your screen on your e-learning yet because I have not turned it on. So assignment number 9. Let me scroll and scroll. Okay. Okay, so let me share the screen. Where is it? Share. Okay, so this is the one, assignment 9, second order ODE. There are two questions in this this assignment. There are two questions, so I think why is it not there? Okay, so this is the one, assignment 9, second order ODE. Because I don't think you can finish this by 10:30. I'll extend this maybe until lunch, until 2 p.m. So please submit it by today. You still have time about half an hour. Okay, please submit this before 2 p.m. Before 2 p.m. because this is a very short assignment. So you can finish it by 2 p.m. today. All right, so I think that's it. Still, you have time to look at this and try to finish this. Try to finish it. I'll change the time. Due date from the due date is today, but from 10:30 maybe to 2:30 p.m. All right. So until next time. Before we go, any question? Before we go, any question? Okay, if there's no question, I think we are going to stop here and continue later. Continue later. All right, so that's it for today. Don't forget, the assignment is due today at 2:30. Thank you very much.